So first discussed about the heat capacities and its two different types, heat capacity at constant pressure and that at constant volume. Now let us summarize the idea of heat capacities for gases, for various groups of gases. So let's begin with the case of ideal gases. So let's recollect. You see, I'm talking about the molar heat capacity. One is the CV and the other is the CP, CV and CP. You know, the CV and CP both are defined. Small CV, right? CV is equal to capital CV by N. That is the relationship that we have. And the same manner I can say the small CP, molar specific capacity at constant pressure, that is equal to capital CP by N. That is a heat capacity at constant pressure divided by the number of moles. So it's our specific quantities, just remember that. And hope you remember from Mayer's relationship, which connects the specific molar heat capacities as CP, small cp minus CV is equal to R. So that was our Mayer's relationship. So let's keep these equations in mind and then come to the description that is given here. So let's take one by one as you have seen. First let us discuss the case of ideal gases. So you know, for an ideal gas, the internal energy is a function of temperature alone. That was our first conclusion. So the background knowledge, you can keep it. The internal energy is a function of, always remember this fact, for an ideal gas, internal energy is a function of temperature alone. And hence, you know, what is the connection between internal energy and CP-CV equations? You know, capital C V, capital CV, whatever relation is for capital CV, the same relation will be holding good for small cv also. So that was defined as dou u or du, also you can write dou u by dou t, dou u by dou t, that is the derivative of the internal energy of the system at constant volume. Okay, so since u is a function of temperature alone, automatically you can say that CV and CP, which are derived from u, will be also functions of T alone. So that is the first thing you have to understand. ഇങ്ങനെയാണ് relation വരുന്നത്. CP and CV are functions of temperature only. So that is very important. They are functions of temperature only for ideal gas. And you know, from Mayer's relation we have proved that CP is always greater than CV. CP is always greater than CV. That is one thing, because CP minus CV equal to R. And second property, you can see that CP minus CV is not a function of T. CP and CV are individually functions of T, but the difference between the two, and that is something very important. Okay, difference between the two, you know, which is given by the Mayer's relation, equal to capital R. So this capital R is a constant. So CP minus CV, the difference is not a function of T, but it's equal to the universal gas constant capital R. And the third one, you know, CP and CV individually being functions of temperature, you can very well expect that the ratio of the specific heats, which are already named previously as adiabatic index gamma, is a function of the temperature T. And since CP greater than CV, the value of gamma will be always greater than 1. The value of gamma will be always greater than 1. So these are some facts that you have to remember regarding the molar heat capacities of an ideal gas. Now let us come to the real gases. Okay, let's classify the real gases into three categories. What are the things? One is monatomic. Remember, it is not monoatomic, it is simply monatomic. Okay, there is no O. Monoatomic alla, monatomic aanu. Be careful about when you write it. It's a common thing that is taken care of. Monatomic, then diatomic, and let's say triatomic, or we can classify it one as polyatomic. Okay, അപ്പോൾ നമുക്ക് ഇങ്ങനെ റിയൽ ഗ്യാസസിനെ നമുക്ക് ഇങ്ങനെ തരംതിരിക്കാൻ പറ്റും. ഇനി ഫോർ monatomic gases, so we are taking some common example like helium, neon, okay, like argon, okay, and not only for monatomic gases like these noble gases, and also most metallic vapors such as vapors of sodium, cadmium, mercury, etc. ഇവർക്കൊക്കെ ഇത് ഈ റിലേഷൻഷിപ്പ് കറക്റ്റ് ആണ്. സോ വാട്ട് ഇസ് ദ തിങ്? First thing, that is Cv is a constant for a wide range of temperature. Okay, that is one thing you have to remember. For monatomic gases, Cv is a constant for a wide range of temperature. So even if you change the temperature by a large amount, Cv practically remains constant. Okay, I will show you a table at the end which shows the variation of the value of Cv for helium, neon, etc. You can see that the variation is very, very small. So practically we treat Cv to be constant. Okay, and remember the Cv for monatomic gases is very close to 3/2 R. That is, remember, this is an experimental fact. Most of the discussion that we are doing now is based on experimental results which were later proved, okay, using kinetic theory of gas and also statistical mechanics. Okay, so Cv is equal to, let me write, Cv is equal to, these are all small c values, Cv equal to 3/2 R. That is one relationship. Second one, what about the Cp? Cp is also a constant for a wide range of temperature and it is very close to 5/2 R. So I can write Cp is equal to 5/2 R. Now you can just look at these two expression, and always you know that Cv Cp should be connected by the Mayer's relation. Okay, so what is the Mayer's relation? Cp 5/2 R minus Cv, which is 3/2 R, and is not the difference between these two is equal to capital R? Yeah, it's holding good. Means these gases should obey the Mayer's relationship. Okay, reason, even though they are real gases, we assume a type of ideal gas behavior. We are assuming a type of ideal gas behavior for these gases also. That is why they are, okay, no, found to be obeying the Mayer's relationship. So be careful about that one. These gases obey the Mayer's relation because they are approximated. Okay, the theory is approximated, assuming that they are what? Ideal gases. Now the ratio Cp by Cv equal to gamma is a constant. Once again, you know, whatever is true for Cp and Cv individually, and you can see, you can take Cp by Cv. So 5/2 is not 5/2 R divided by 3/2 R. You know what will come? 3/2 R. So the R and R getting cancelled, 2 and 2 getting cancelled. Finally you are left with, it's equal to 5/3. And you know how much this 5/3 will come? This 5/3 will be almost some 1.6. Okay, roughly 1.66 can take. But remember, it varies from gas to gas, and it varies. It has got a slight variation with the temperature for the same gas. So let me take it as roughly as 1.6. Okay, so that is regarding monatomic gases. Now just let's go to the other case, which is for diatomic. Same manner I can discuss diatomic gases. So see that in diatomic gases you have to give a special attention. What is the special attention to be given? See, let's see what are the examples. Air. See, air is given to be an example. Then hydrogen, oxygen, nitrogen, nitrous oxide, carbon monoxide, all these are diatomic. Okay, only 2 atoms are there. Now why do we consider air, which is actually a mixture of several gases, also as a diatomic gas? It's very evident. Why? Because you know, air, our atmospheric air, what we mean, air is predominantly a combination of nitrogen, which is around 78%, and the remaining is what? Mainly oxygen. Okay, so nitrogen and oxygen make up almost 98% of the atmospheric gases, you know. So since the main components of atmospheric air are predominantly diatomic, we consider air, which is actually a mixture of gases, also as what? Having a diatomic behavior, and that has been experimentally verified. So that is one word of caution for you while you are doing problems. Okay, suppose that you are given a problem to calculate the work done during some process, okay, say adiabatic process, and you are not given the value of gamma. Okay, instead it's mentioned that certain quantity of air is compressed adiabatically, or air is expanded adiabatically. Then you recall that the gamma in that problem will be the gamma for diatomic gases. Already I have given you one problem, I think, in the problem assignment 1, the problem of air. So whenever it is air, remember air has to be treated as diatomic, whose gamma value will be then the value for diatomic gases, which we will be just discussing shortly. And you know the value. Okay, so let's see what are the specialities for diatomic gases. So for diatomic gases, let's once again see Cv is a constant at ordinary temperatures. See that at ordinary temperatures, very near to room temperature, Cv remains practically a constant, and it has been experimentally observed that it nearly equal to 5/2 R and increases as the temperature increases. So the value of Cv increases with increase in temperature for diatomic gas. That is a usual observation. So I can say the Cv is small c. Remember, I am using small Cv actually. Cv is approximately equal to 5/2 R. That is one thing. Just note these values. I will come back to these values in a later topic on degrees of freedom. Now, Cp is a constant at ordinary temperatures and nearly equal to 7/2 R. I think with a little bit of logic you can understand what will be the value of Cp. Okay, so Cp is equal to, I can say, 7/2 R, and it should be like that. Why? Because once again, considering an ideal gas behavior for such gases, they are bound to obey the Mayer's relationship, which says that the difference between this Cp and Cv should be always equal to capital R. So once you remember one of them, you can easily predict what will be the other value. That's the advantage of remembering the Mayer's relationship. Okay, now of course, can't you say what will be the ratio gamma? Gamma will be equal to Cp by Cv. So what will be that? It will be equal to 7/2 divided by C5/2, which is nothing but is equal to how much? It will be equal to 7/5. 7/5. You can say it's coming roughly around some 1.4. Okay, 1.4. And this is the value, okay, 1.41 or so. That is a value that is usually given in problems of adiabatic expansion of air. Okay, so or any other diatomic gases as such. And see that it is very close. There is a specialty. It is constant at ordinary temperatures and is very close to them, and it decreases. Okay, it decreases as temperature increases, and that is the the relation that is given for that. Okay, now polyatomic gases. Let's come to the case of polyatomic gases. In the case of polyatomic gases, means it can be triatomic or more than 3 atoms. So CO2, ammonia, NH3, CH for the methane, the chlorine, the bromine, all. Okay, no, just actually I think there should be some. I hope that this particular 2 examples I didn't note that. We have to see. I have a doubt with these 2 examples, Cl2 and Br2. I don't know how it is. Okay, let's verify that later. Anyway, all these triatomic and higher, okay, they are all having Cp and Cv, okay, and they and gamma vary with temperature, and the variation is different for different gases. That is in general. And the value of gamma shows a actually large variation. Actually, the value of gamma shows a large variation, and see almost from some 1.1 to 1.3, 1. Okay, like that it goes. So usually the standard values we will take that gamma for polyatomic is something around 1.2 to 1.3. Let's take 1.3. In books you will see some 1.33 and all. That you cannot say actually exact, because it depends on the particular gas sample, and also it varies with the temperature. So be very careful about it. So why this 5/2, 3/2, 7/2 are, we will connect it with the degree of freedom, that is later. Just remember this one, okay, that it is some these numbers, please keep in mind. 3/2R, one was this one, 3/2R, that was for monatomic. Then you have seen some 5/2R sequentially, and then you have seen some 7/2R. I need okay, these values. See, note these values for time being. 3, 5, 7. Okay, 3, 5, 7. 3 denotes 3 translational degrees of freedom. 5 denotes 3 translation degrees of freedom plus 2 rotation degrees of freedom, and 7 denotes 3 translational, 2 rotational and 2 vibration degrees of freedom, which changes with temperature. I will discuss about degrees of freedom at the end of this topic. Anyway, only for reminding you, I have just made a mention of that one here. So I think that is something relevant that we discuss the molar heat capacities of gases. Now let me just end this session discussion with just showing you a table, the variation. I have taken this one from Wikipedia. See, let's try to verify. I think such a data analysis will be helping you in remembering the data better. Like, let us first sort out. So what is given here? It is temperature given here, the gas sample is given here, and its adiabatic index gamma is given here. Okay, so let us sort out first the monatomic. So here comes helium, right? What is the value for helium? Yeah, monatomic, one atom. So 1.66. Just verify. Sorry for the trouble, just a moment. Okay, like for monatomic it is 1.66. Like, let's take what is the first next one. It is argon. See that, just see the note the difference there. Argon, it is minus 180 degrees Celsius. Remember, you have to consider both the temperature as well as the value. For helium, the data given 1.66 at 20 degrees Celsius. Okay, which is near to, you say, the room temperature. But the argon data that is given here, first one is for minus 180 degrees Celsius. So do not be worried about this value. Just look at the next value. Okay, for the same argon, see, argon 20 degrees Celsius value is given here. What is the value? It is 1.67. And can't you see that is very close to 1.66? That is for helium. So 1.66, 1.67. That is the data. Now let's see whether there is any more monatomic. Yes, I think. Yes, you can see neon is there, xenon is there, krypton is there, and also they talked about metallic gas vapors. Here mercury is given. So all these values you can see from the table. It is very close to 1.6. So let's say that for monatomic, at least you remember, at least at very near to room temperatures, its value can be treated as 1.6. This is the experimental data. Remember, these data are experimentally measured data. Okay, and it has been found consistent with the theoretical predictions. So now the diatomic gases, let's start with hydrogen, the common diatomic gas. So hydrogen, you can see the value for gamma at minus 181 degrees Celsius is 1.59. But see, when the temperature increases, minus 76 is 1.45. 20 degrees Celsius, I'm trying to compare the data available at 20 degrees Celsius. It is 1.41 for hydrogen. Okay, now let us take which other thing? Yes, please. Here you see dry air, that also you please see. Dry air 0 degrees Celsius. Yeah, let's spot out 20 degrees Celsius. It is once again 1.40. So 1.4. Then O2, oxygen minus 181 degrees Celsius, 1.45. And you can see like as the temperature increases, it has become 20 degrees Celsius. It is again 1.4. So likewise, you can just nitrous oxide also 20 degrees Celsius data you can see in most. See, for a nitrogen N2 20 degrees Celsius, it is 1. Okay, sorry, this is not for N2. This is for Cl2. Of course, the data shows that Cl2 is also having. Maybe there are some exceptions, like we have seen the case of mercury gas. Similarly, there may be some exception for chlorine gas, even though it is diatomic. I don't exactly know the chemistry behind it. Please try to search for it. Cl2, it is 1.3, near to that of polyatomic. Okay, now, so that is about the thing. Now I can, so roughly I can say for a diatomic thing we can take gamma value is near to 1.4. Okay, and for a polyatomic you can see from the data for water, yeah, for water 20 degrees Celsius, for water it is what, 1.33. Yeah, I think from only from this particular table I'm getting an insight. Okay, you can very well remember the data for triatomic or polyatomic. Why? Just remember the case of water. For water, gamma is equal to 1.33. What other value is 1.33 for water? Hope you remember, this is nothing but the refractive index of water. See, that is a pure coincidence. I just have noticed that one right now, but remember, I think it will help you to recall two important facts. One thing, you can remember the refractive index of water, that is 1.33, that you are doing in liquid lens experiments. Other thing, from this analysis you got another concept, that the gamma for water, which is a triatomic or a polyatomic system, water vapor of course it is, yes, that is, remember that's one thing, it's H2O means water vapor, that also is what just 1.33. so now other things also you can just compare. CO2, you can see here it is given CO2 20 degrees Celsius. Remember, when you make a comparison you have to compare it under same situation. That's why I'm trying to spot out 20 degrees Celsius, then only you will get a clear idea. No, you have to keep one property constant and then compare other properties. That is a method of science. Okay, you cannot compare the value of gamma for hydrogen at 100 degrees Celsius with the value of gamma for nitrogen at say 20 degrees Celsius. Either a temperature has to be maintained constant and then compare the gamma values, or otherwise. Okay, right, so that is about the thing. So you can see that it's all near to some 1.3. yeah, for say methane, you can see for 20 degrees Celsius it is 1.32, and so on and so forth. Okay, and can't you see something very significant here? See that it is for C2H6 and all, it is 1.13. there is a lot of variation, 1.22. okay, a lot of variations are there. When it is polyatomic, it will depend slightly. Okay, so I hope that the discussion was useful, and always remember, this is my conclusion. Gamma for monatomic, is greater than gamma for diatomic, greater than gamma for polyatomic. This is the thing, right? So hope you remember we had a question in the test review quiz where it was given the two curves corresponding to two different gases. These two are adiabatic curves, correspond to different gases, and you are asked to find out which one corresponds to monatomic, which one corresponds to polyatomic or diatomic. So now you can clearly understand that the slope is directly proportional to gamma, right? Okay, so you can just see it will be in the order of monatomic, then diatomic, and polyatomic. Okay, so you can just in the order that you can clearly predict. Okay, so that's about the discussion of heat capacity for various gases. Just see that these ideas are very, very relevant for your higher studies as well. So focus on this topic, memorize the values wherever needed, and do apply in your problems. Okay, thank you.